I just made the transition from snow boots to high heels, and I'm feeling a little nervous, but I made it up here okay. Hello, I'm Rachel Cave, and I work for CBC News in New Brunswick. And I'm a little shorter than most, and I hope this is okay for you, Dr. Masry. You may need to lift it up in a minute. But this presentation is called Mapping the World's Oceans. It will be presented by Dr. Mark Masry, Manager R&D, CARIS. And after the presentation, Dr. Masry will take questions, and we will receive them by Twitter, so please be sure to get your questions ready. Dr. Masry received his B.Eng degree in electrical engineering from the University of New Brunswick. That was in 1998. He received his doctorate in electrical engineering from Cornell University in 2003. He was a postdoctoral researcher in the Computational Synthesis Lab at the Sibley School of Mechanical and Aerospace Engineering at Cornell, where he worked on image understanding and computer-aided design. His research interests include spatial data structures, visualization, signal processing, and image understanding. And he joined his father's company in 2006, and he now manages the company's research and development work. Please give a warm welcome to Dr. Masry.
One too far. I'd like to talk to you today a little bit about some of the work we do at CARIS and some of the work I'm involved in, particularly on the subject of ocean mapping. So this is kind of an interesting topic. It's one that we do an awful lot of. We build software tools that facilitate the mapping process, and there's some interesting work involved in the storage of large data volumes, processing of large data, and actually producing these maps of the ocean. So first of all, why are we even interested in mapping the ocean? Well, the ocean is actually one of the great kind of undiscovered frontiers of the world. It covers 2/3 of the Earth's surface. It's the largest single connected feature on the planet, and yet we know almost nothing about it. In fact, we have mapped less than 10% of the ocean floor, and when I say we, I mean the military. The public actually knows less than 2%, or between 2 and 3% actually. Of the ocean has actually been mapped in any kind of publicly understandable way. And this is kind of a tragedy because the ocean actually is of such importance in terms of shipping, in terms of our food supply, in terms of weather, and basically it's such a critical part of the world that we know nothing about. And since the population is growing and we need more resources and more space, it's kind of imperative that we should understand this massive, massive frontier. And in fact, our lack of understanding is such that some people say we have better maps of the surface of the moon and the surface of Mars than we do of our own ocean. So to begin with, what is an ocean map? Well, this is what an ocean map looks like. This is actually a nautical chart that was developed by the Canadian Hydrographic Service, which is part of the Department of Fisheries and Oceans. And you can see that what it really is kind of a distillation of information. These charts are really interesting because they take huge volumes of data and kind of render them down into a form that's comprehensible by mariners very, very quickly. So they present very detailed information in a way that somebody can grasp in very difficult conditions. And the reason for that, of course, is that the marine environment's a harsh one. And if you have to make decisions quickly, you need to be presented with the information in a way that allows you to do so. And so these charts are actually made to very strict standards. They're built around a set of conventions and a set of symbols that are easy for people from all countries in the world to understand because, of course, navigating the waters is an international pursuit. And they convey a lot of information, particularly about safety. The two things, or actually the three things really you need to understand on any chart are: one, your position horizontally, or where you are in the world; two, the depth below you; and three, the features around you. So I'm going to talk today primarily about the first two things, the depth and the position, and how we build tools that actually allow some of these charts to be created. So this is a really old chart. This is a nautical chart from, I think, the 1400s. What you can see here is that in comparison to the previous chart, there's very little going on in the water. There's a lot of sight lines. There's some magnetic, there's some sort of magnetic compass information, but the actual depth information that would be present on a modern chart isn't present at all. So someone trying to navigate using this would have a rough idea of the shape of the coastline and of some particular sight lines they could use, but would have absolutely no idea what was under them. And of course, when you're aboard a ship, what's under you is of critical importance. And in fact, some of the more artistic charts of the time actually had sketches of sea monsters and other sorts of really kind of interesting sort of Pirates of the Caribbean type stuff on it, which wasn't actually very critical for safety of navigation, but was interesting and kind of entertaining nonetheless. So, but you can see that this is kind of a very different sort of flavor than what we might be used to now. And clearly there was no sort of standard about how to make these things. Everyone was kind of on their own. Every country did it differently. And it was almost really a work of art. In fact, actually, the Inuit have a kind of chart as well that doesn't even require paper. In fact, they essentially carve out the coastline on a piece of wood, and then they trace their finger along the shape of the coastline as they're moving around to figure out where roughly they are. So there's all sorts of different kinds of chart, and they kind of depend a little bit on what you're trying to do with them. But certainly the older technology is, the less detail you get. So the two key things to understand in terms of positioning, in terms of where we are in the world are, for the purpose of this discussion, is latitude and longitude. The longitudinal lines are the ones that run sort of north-south, and the Greenwich, and they look a lot like time zones, actually. So in fact, like Greenwich Mean Time, relates to the study of longitude, or to the sort of the longitude you're at, excuse me. So we'll actually come back to the notion of time a little later on. The other important measurement is latitude, which is where you are north-south, and the latitudinal lines run parallel to the equator. So the first attempts to actually measure your position, to estimate where you were, used something called dead reckoning, which was a very sort of primitive estimation technique. Well, actually, it's not really primitive. I'll come back to that. But basically, what you would do is start at a known position, which is called a fix. And you can see here that we have fix 1 along a coastline or a land feature, where you knew where you were. And you would measure your attitude and your speed and attempt to estimate, based on how long you'd been traveling, where your second position was by updating the first one. And then you'd kind of rinse and repeat. So you'd go fix 1, fix 2, fix 3, and so on. The problem with this is that, of course, your errors propagate over time. So the more steps you take and the more fixes you have, the more likely you are to have some kind of error in your position. But in spite of that, modern systems, modern inertial navigation systems, still use dead reckoning in a way, because the sensors are good enough that they can actually estimate their position correctly with a minimum of error in such a way that the propagated error isn't too bad. And the guidance systems on a lot of missiles or armaments or different kinds of robotic devices often do use inertial navigation, which is a form of dead reckoning. So this didn't work all that well in terms of estimating position precisely for the ancient mariner. So basically, there was a big effort underway to try to figure out how to estimate your position when you didn't have a frame of reference, when you were just out at sea and trying to figure out where you were. And so the first estimates really revolved around the use of, or the attempts rather, to measure latitude, which is, as I mentioned, the lines that run parallel to the equator. And the attempts to do this usually involve trying to measure the angle between the sun and the horizon, or the stars and the horizon, which is called celestial navigation. And one of the tools that was used to do this is the sextant, which you see here. And the sextant can also be used to measure the angle between two sight lines on the shore, and you can use triangulation then to figure out exactly where you were. But this still didn't address the question of longitude. And in order to measure longitude accurately, there were ways of doing this using celestial navigation, but a lot of the most accurate measurements, or most of the prevalent measures of longitude, related in some way to time. So actually the creation of timepieces sort of heralded the modern age of navigation in a way, because these timepieces allowed you to measure the time where you were relative to a known location. And because the longitudinal lines, as I mentioned, do kind of resemble in a way the time zones, and if you knew roughly what time it was back home, and you knew the position of the sun at noon Greenwich Mean Time where you were, you could actually use that to estimate your longitude. So now you know your latitude and your longitude. And these timepieces were so important that they were actually maintained by sailors whose job it was specifically to do that, to calibrate them, to keep them wound, to measure the errors, and to estimate the errors over time. And they were of such expense that they actually were a significant part of outfitting a ship was actually provisioning it with timepieces. So it was a very, very big deal. And the first sort of seaworthy timepiece, or the one that really kind of cracked the problem of measuring time, was invented in, I believe, 761 in response to a sort of prize competition that was held by the King of England at the time. So it was of such importance to the Royal Navy and to marine commerce that they actually held a prize that I think was worth several $1 million in today's money for the first person who could invent a workable marine chronometer. The other question, once you know your position, then, as I mentioned, the big question is really depth. How much water is under the keel of your ship where you are? And what you're looking at here is a diagram of sort of the number of different depth offsets rather that might be interesting or that are of interest when you're attempting to compute your depth at a given position. And you need to know not only the underkeel clearance, but you need to know the tide, you need to know how much draft your ship has, and you need to know all these things because if you are piloting a huge ship, the amount of clearance under keel and the tide becomes very, very important. This vessel is called the Emma Maersk, and it can carry 170,000 tons, I believe, of cargo. And what happens is that this vessel is so big that it can't actually navigate into certain ports. And when it does navigate into certain ports, it needs to know precisely the amount of underkeel clearance because that will regulate the amount of cargo that you can put aboard the ship. So in a very real way, depth is money, because if you put too much cargo on the ship and it rides too low in the water, it can run aground. And of course, that can be costly too. So basically, in other words, a lot of captains have actually described piloting one of these things to piloting a 747 very slowly, but a couple centimeters off the ground. So it's a very, very precise kind of activity. So how do you measure depth? Well, the initial measurements of depth were conducted as you might think. You take something very heavy, attach it to wire, and drop it over the side of the ship, and then actually lower it down and measure how long it took to hit the seafloor. And often they would record a sample of the seafloor. There was kind of an attachment that could grab a little bit of soil and bring that back up. And the first measurements of depth that were recorded were in around 1840. Those are the first recorded ones, although obviously people had been doing this for quite some time. And then they recorded one or two measurements on a single survey cruise, because it was quite a laborious process to do this in any kind of deep water. Then by about 1853, a single survey cruise could record about 100 depth measurements. And then after that, around I think one of the biggest cruises recorded several hundred. By about 1920, there were 16 to 17,000 known measurements of depth below 1,000 fathoms or below a certain level. And then everything kind of changed. And so that's where I'm going to introduce kind of the modern part of the story. So there were three big inventions that changed everything for people. The first was sonar, the second was vessel positioning sensors, and the third was global positioning systems. And you're probably familiar in some way or another with some of these systems. So I'll talk a little bit about each of them, and then I'll tell you a little bit about what we do with the data that comes off these systems. So sonar is basically the use of sound to measure your actual depth. And it works essentially the way a gigantic speaker would work. It projects a sound pulse into the water, and it measures the return in some way and uses that to characterize the depth of the seafloor. And this is actually kind of a tricky problem, because as the sound wave propagates through water, it obeys Snell's law, and it can refract through these different kinds of temperature and salinity gradients, and especially pressure gradients. And so characterizing the water column itself becomes kind of a difficult problem. But if you can characterize the water column, and you can measure the sound accurately, then you can actually estimate your depth from sonar. And so the first sonar that was actually deployed aboard ship was deployed in the early 20s. And in a single voyage, it managed to collect 5,000 measurements of depth. And then in 1925, a German ship called the Meteor collected 67,000 measurements of depth in a single voyage. So this is a gigantic increase in data over what was previously possible with lead-line systems. And in fact, there's two kinds of sonar. There's what's called a single, well, there's many kinds of sonar, but there's two. The early sonars were really what were called single beam systems. In other words, there was a single sound pulse, and it was used to generate a single measurement of depth. Modern sonars are called multi-beam, or a lot of modern sonars are multi-beam sonars, which means that there are several beams, in other words, several measurements of depth that can be collected from a single sound pulse. And these systems, the modern ones, can have up to 508 measurements from a single sound pulse, and they can pulse relatively quickly. So you can generate vast amounts of data. And in fact, handling all of that data has kind of become the problem. But it's not enough simply to know the depth. Actually, before we go on, I'll just show you roughly what this looks like. This is kind of called mowing the lawn in a way, and it works just sort of the way you might expect. A ship will sort of pass over an object or an area of seafloor that they want to survey, and they'll use these multi-beam sonars, and they'll record depth measurements as they progress along each line. And the goal of the survey generally is to cover the seafloor that you're interested in with enough coverage so that you can get a high-resolution picture of the seafloor below you. And so in this case, there's actually, it appears, some sort of wreck or object on the seafloor. The second important thing is vessel positioning sensors. So there's three kinds or actually there's three important measurements around the vessel's axis system, because the sonar is actually mounted on the hull of the ship, so it's relative to the position and the actual direction and pitch, roll, and yaw of the ship. So you need to know those things as well in order to sort of start to reference the data in something more than the ship's coordinate system. So the pitch is the motion of the ship on the waves, the forward and back motion. The roll is the oscillation of the ship around its central axis. And the yaw is the twist, rather, of the ship around its z-axis. And you need to know those three things in addition to the measurements that come back from the sonar to start to begin to position the seafloor with respect to the ship. But it's not enough to position the seafloor with respect just to the ship. You also need to know where the ship is, and that's where the GPS system becomes important. So GPS obviously stands for Global Positioning System. Many of you are actually carrying around global positioning receivers in your phones nowadays, which tells you a bit about how far we've come. They used to be very, very large, bulky systems to install and maintain. And in fact, I think that the first commercial GPS, or the first declassified GPS, was declassified by Reagan in 1980, if I remember correctly. So for a long while, it was very hard to even use GPS to get an accurate measurement because the military restricted the precision of the measurements that could be made with the GPS systems that were available. But now, using a differential GPS, you can actually measure your position to within several centimeters horizontally, and you can also measure your vertical height on the Earth's surface to within a decimeter or so. So you can get very, very accurate measurements. So where we come in, actually, and actually just to give you an idea here is of the hydrographic processing data flow and where CARIS comes in. This essentially what happens is these three sensor systems, the vessel position, the sonar, and the GPS, are all fed into a processing engine of some kind that generates a huge series of raw georeference data points, which we call a point cloud. The point clouds are then turned into a model of the underlying seafloor, and that model is used to generate a nautical chart. And I'll talk a little bit about each of those pieces. And so CARIS actually makes the software that does the latter part of the chain. We don't make the sensor systems themselves, but we do take all the data that they produce and run it through this pipeline, which we kind of call the ping-to-chart pipeline. And the company, as was mentioned, was started about 30 years ago by the other Dr. Masry. And we've been around for 30 years. We started in the geomatics industry, and we still do GIS software, but a lot of our work now is in marine software. And if you've been aboard a ship or you've actually used cargo that's been transported on a ship, which is pretty much everybody, you've probably been influenced in some way by data that's passed through one of our tools. And in fact, all of the charts produced by the Department of Fisheries and Oceans and the Canadian Hydrographic Service are now produced with CARIS software, as are all the charts that are produced by the Royal British Admiralty. So we're located here in Fredericton. We always have been, and we always will be, I think. CARIS headquarters is on Wagner's Lane, and we're very proud to be here because the city's been absolutely great to us. It has a very vibrant IT community and an excellent infrastructure, actually, as well. And we're well hooked into that, and we benefit greatly from our presence here and from the people who we've been fortunate to have a lot of really, really great people, many of whom have come from the region, and many of whom have come abroad to live and work here. So we've definitely benefited from our time and from our presence here. So the data flow itself begins with, as I mentioned, this kind of idea of a volumetric point cloud. I won't get into too much of the math or too much of the actual processing tools that were used to georeference all the data. But once you take these three sensors and feed them together, what you actually get out is a massive cloud of georeferenced points. And what that means is that every point knows its X, Y, and Z position in space or in the world. And we can put them all in one gigantic repository, which we call a point cloud. What you're looking at here is a bunch of single beam echo sound or track lines that were registered by ships as they were crossing the ocean, where they just left their sonars on, and they just recorded data points as they went. And then we georeferenced those and kind of concatenated them all into one gigantic file. And what you can see is that all of these track lines form individual lines, but they kind of converge around the island mass that's in the center. And so you have much more data in that area because that's where ships were coming into dock or where they were navigating around the edge of this island boundary. But typically, a lot of our data kind of either looks like this, or it looks like the much more detailed multi-beam surveys of the seafloor. So I'll actually show you a video of that now. So this is a point cloud that was made from a multi-beam survey, and what you can actually see is the outside boundary of several different swaths as they overlap a particular piece of the seafloor. This is the raw data. You can see many of the features that are actually on the seafloor, and this is before we've even done much processing on it. And you can pick out individual rocks, and you can even, if you look closely enough, I'm not sure if you can see it on this monitor, but you can actually see the individual beam lines as they they move along the seafloor. So it's kind of interesting that this data you can actually almost produce in real time. As the ship's moving around, you can start to collect these data points because all these sensors are mounted on one ship, and usually a lot of the correction and the georeferencing can be done aboard ship itself. And so you can almost see, and it's incredibly quite detailed. There's a lot of pockmarks and different features on the floor to observe. So this is kind of where everything starts. And these clouds can be very, very large. So we can have single clouds that are several billion points in size, and we anticipate that the volume of those clouds is actually going to keep getting bigger and bigger and bigger. The sensors are getting more and more powerful. The amount of data we're collecting is more and more, and we're doing less and less decimation now. People are interested in keeping more and more of the raw data as much as they can. So how do you construct a model of the surface? Well, in very simple terms, what you can do is construct a grid, and then you can build a mesh over top of it. So the goal here is to take these raw data points and actually make them into a representation of a continuous surface. And you can do that by triangulating a bunch of points that are on a grid. You can also triangulate the points directly, or you can use regular points, but for the purpose of this discussion, I'll just talk about the grid. So the trick here is that in every point in a grid is actually spaced out the same distance from its neighbors as any other point. And so once you set up the initial grid and you construct the mesh between it, you then have to run some tools to actually estimate the value of the depth at each position in the grid. And that will give you a model of the underlying seafloor. And the way you do that is by looking at an individual grid value and taking all of the sort of sonar data points, the raw data points that are around that value, and using something like an inverse distance weighting or a Kriging mechanism, or there are other tools as well, to estimate the value of that grid point. Now there's also another factor here, which is that the sensors themselves have error in them, or they have an amount of uncertainty because they're complex and because you have to combine all of them in a fairly complex way. So you can actually estimate the uncertainty of that measurement as well. So you can say that this value is 100 meters below the seafloor, and I know that to within 2 or 3 meters. Okay? So, and typically that becomes very, very important because, again, for safety of navigation, you want to know sort of the outside envelope of this surface because you want to avoid running aground. So after you've constructed a grid, you can visualize it. And what you're seeing here is actually a grid stored in one of our file formats, which is it's structured in such a way that it allows for fairly easy visualization. And we're just going to fly down. I've gridded some of the data that you saw earlier in the point cloud. This is actually a different section of it. And you can actually see the model of the seafloor. And I've done some other things too. I've turned on shading and I've turned on lighting. And you can see yourself moving around the seafloor. And this picture can actually be generated very, very quickly from the raw data. In fact, again, you can almost begin to do this at sea now. So you can see various features. You can see the contours of the seafloor, and you can start to see, in a way, the coloring is done by depth. So blue regions are deeper than the other regions, and yellow regions are higher. You can almost start to see the outline of where some of the features on a chart might lie, and then the question then becomes, well, what areas are which depth? So there's another problem as well, which is that we want sometimes to represent, a regular grid is very nice, but sometimes we want to be able to represent data at slightly denser resolutions in areas where we know more about the data, where we're more interested in certain features, or maybe in shallow water we'll have more data because the sensors are closer to the seafloor and they can measure data more accurately. In deep water we might have much less data. So we've been working on something which is sort of a variable resolution grid. In other words, the resolution changes across the surface of the grid. And to give you kind of a toy example, this is a variable resolution grid in a checkerboard pattern where every checkerboard square has a slightly different resolution, but the whole thing is actually stitched together into one large triangulation. So it's actually fairly easy to do this for small numbers of points, but the real challenge becomes in dealing with the volumes of data that we have to deal with to construct something like this that I can actually move around, navigate, visualize in 3D, inspect, and run computational tools on. So that's kind of some of the work that we're doing a little bit now, and that involves working with data structures, working with spatial query techniques, and actually working with meshing techniques to build the mesh dynamically. And we have to do all of this fast enough so that someone can actually open the file, interrogate the data, fly around it, and make a decision about what's there and whether or not they want to submit it for further processing in a relatively short amount of time. So as I mentioned, the volumes of data we deal with really are huge. In fact, some of our grids, to give you an example, are hundreds of thousands of nodes in width and hundreds of thousands of nodes in height. And so to give you some idea, if you take a photo with a high-end digital camera, it's about 25 megapixels maybe or better, which is about 5,000 by 5,000 pixels. And our grids can be 20 times as large on either dimension, so it's about 400 times the size in a single large grid. So to deal with that data, we have to build various tools and techniques. One of the things we do is that we built an IO-efficient subsystem, which is actually a way of handling this data in a way that models the underlying storage system efficiently. And we take all this data, which is spatially organized, and we break it into blocks, or chunks we call them. And then we efficiently serialize the chunks to a file system, a database, or some sort of server that's actually out on the network. And we can do this in 2D and 3D. So the problem of partitioning something becomes very, very important. And fortunately, spatial data sets are really good at being partitioned because the data is actually organized in a way just by being organized in space. When you know where the data is, you know roughly what your neighbors are, and that makes things easy to partition. Another technique we use, and this is one you're probably all familiar with if you use Google Maps, is this notion of multi-resolution. So everything we do is represented at different levels of resolution, and we do that because when we want to open a very, very big data set, you want to open a sort of coarse representation of that data set first, and then you kind of drill down into an area that you have more interest in. And the systems we've built up are structured in such a way that that process is quite smooth and transparent to the user. And we call that whole system our sort of our CAESAR or our CARIS data handling framework. And so it sits in the back end and it translates blobs of data between a storage system and the computer. It has several layers of caching built into it and several threaded processing engines that actually fetch and retrieve that data in the background as things are going on. So developers don't really have to care too much about where the data is or how to get it. They just sort of issue a request for it and the system kind of brings it in for them. So it makes it pretty easy for them to build applications on top. So once you have this kind of surface model, the thing you do then is to build a sort of vector representation. So as I mentioned, charts are really a distillation of this huge amount of data into something that's comprehensible to the mariner. And without getting into too much detail about it, one of the simplest vector to model the vector operations that we use is contouring. So you can see here all of the different height shaded, or rather depth shaded values have been transformed into a vector representation that essentially tells you what areas of consistent depth there are. And these vector representations and some of the other data points that are found on the model are actually used to build the chart you saw earlier. And you can almost literally see the depth areas that are in the center of the waterway. You can see areas that are unsafe, and you can see areas that are closer to shore. And that information is critical to the mariner. And you can use the same process to identify rocks, to identify obstructions, and to identify potential hazard areas that mariners might not be interested in, or actually might be very interested in. So now I just wanted to kind of wrap up by talking a little bit about 5 kind of important trends in general that I think are going to affect us and the work we do in the coming years. And the first, as I mentioned, is this kind of notion of increasing sensor bandwidth. So, and actually, the second rather is that we are now producing sensors that are accessible to more people. The third is that we're looking at autonomous vehicles. The fourth, that we have the internet everywhere. And the fifth, that we have distributed processing that can be applied to these problems. So I'll talk a little bit about each one of these things. So the problem of increasing sensor bandwidth is really that the volume of data is increasing more or less exponentially over time. So we started by having about 100 soundings per survey and in the 1800s, migrated to about 20 or 30,000 soundings per survey in the mid-20s, and now our modern sonar systems, which have 508 beams and can pulse very, very quickly and are hooked to a very, very high-speed network aboard the ship, actually are capable of collecting billions of soundings in a single survey. And so to deal with this volume of data, a survey ship will actually install a SAN system, or a storage area network aboard the ship, with racks and racks and racks of drives, and actually record all this data on these drive racks, and then take the racks off when they dock. So there's huge, huge volumes of data. So what this means really is that you can also pick out more stuff in the data. So we're also not only interested in just making a higher precision map or a more accurate map, but we're also interested in picking out different features. So the sonar systems, it turns out, can record more than just the depth of the seafloor. They can record information in what's called the water column itself, which is that body of water between the seafloor and the sensor system. And what you're seeing here is a gas plume, which is a massive gas floating in the water. And this measuring this kind of thing, quantifying where it was, became extremely important during the Deepwater Horizon event, which was where a lot of this sort of modern water column processing stuff was really used heavily. So they would actually run sonar surveys of the area where the leak had occurred and use the sonar systems to pick out these sort of volumetric clouds of gas plumes and measure them and study them in the water. And so part of this sort of increased volume of data that's coming back is that we can actually extract more from the data. We can do more with it. So that's going to become very, very important to us. And we have to build the systems that are kind of capable of handling it. So some of the groundwork that we've laid so far is actually intended to be able to address these kinds of problems and to allow these data sets to be visualized and managed effectively. The other thing that we're seeing is that these sensors are becoming a lot easier for people to use. Just as with the camera market, which started with very complex, kind of cumbersome and expensive cameras and then graduated to very small devices that you are literally now carrying around with you and you can use to take pictures, sonar systems are becoming a lot easier to use too. It's a lot easier to install one, it's a lot easier to manage one, and a lot more people actually have these systems. In fact, in simple form, almost every pleasure craft has some kind of simple sonar system. And this has led to a development called, or actually the use of crowdsourcing to produce nautical charts. So this is actually generated from a website called OpenCMap. And OpenCMap is a crowdsourced website where everybody uses the sensor systems on their pleasure craft and actually records data and feeds it onto an online site and generates a chart from their own data. And so this effectively is not something that's been certified as being safe for navigation, but it is something that people are starting to use more and more. The other issue, or the other thing we're seeing happening a lot, is this sort of rise of autonomous vehicles. So people are building submersible devices that can operate completely independently of the main ship. They can run for extended periods on battery power, or they can be powered by solar power. And they can actually do small amounts of sensor measurement, small amounts of data measurement completely autonomously from the main vessel, and then transmit the results back. So this has enabled a lot of different kinds of surveys that we've never seen before. In fact, you could imagine a scenario in which people deploy a lot of these things in a port to actually constantly measure the amount of silt that's built up in a port and make automatic decisions about where to do dredging or where to remove that silt. And this terrible diagram kind of it sort of suggests that basically the internet has become ubiquitous. And so I was on a ferry crossing from St. John to Digby, and it was a 3-hour crossing at which I was out of sight of land, and at no time during that crossing did I actually lose a high bandwidth internet connection. I was able to do work and surf the web while I was at sea. And so this means that the data that's being collected by these sensor systems can be transmitted back to land or back to a main server center very, very quickly. And in fact, in that main server center, you also have the sort of trend towards being able to do distributed processing of these masses of data. And so distributed processing is just very applicable to problems in spatial data processing because a lot of spatial problems are what's called embarrassingly parallelizable, meaning it's very, very easy to parallelize them, to break them up into bits and transmit them across multiple systems and then bring the results together. So all of these things kind of point to a really interesting convergence towards something that we're starting to call, I think, the living chart, which is a kind of domain in which all of these systems are constantly bringing back more and more data, and they're doing it in such a way that they're always connected and they're talking to each other and back to our central servers, and so they can actually effectively update charts at a faster and faster rate, to the point where some of these charts may actually, we may wind up seeing charts that are constructed in near real time with some kinds of automated quality measures. And this becomes really, really interesting for navigation and also for exploration, because it means in a very real way that we have this kind of flow of data that's always accessible to us, that's always measured by us and understood by us. And so in a very strange way, it kind of means we have a real presence in the water in a way that we simply never had before. Thanks very much.
So we started receiving a lot of questions as you were starting to wrap up there. And the trend I see in some of these questions, I think, is ownership, proprietary questions, like who owns the information now and where is that going?
That's actually a really tricky question. I think my mic fell off here. It's actually a really tricky question. The ownership of this data it's something that we kind of struggle with all the time. Like, for instance, a lot of our clients are military organizations or government organizations who simply don't want to give a lot of their data away. And so in the case of a data set that would be produced by the NGA or by the CHS, the ownership is really with the government itself. In the case of something like the OpenCMap data or the OpenStreetMap data for land, the ownership is really with the repository online. But the migration of data between these two places is something that's really, really tricky.
Well, how do you, so for example, somebody's wanting to know if it goes beyond commercial use, if it goes beyond military use, and you were talking about everybody having access to more sensitive sonar equipment. At what point will it become sort of a wiki, a wiki kind of thing?
Well, I think we're seeing a little of that now, actually. That there are some sort of sites that are actually updated with public-facing data, and a lot of government organizations have started to just give away parts of their data while retaining parts that are obviously more sensitive for themselves. So I think it'll be a progression to where we have a kind of an open set of data that everybody can use, but maybe the higher, the more precise data, the more accurate data might be private for still some time.
Somebody wanted to know if there is environmental protection application for this technology.
Well, definitely. I mean, once you have a map of a particular region, or you understand a particular region, you can do an awful lot in terms of environmental protection. Because in order to actually protect something, you first kind of have to understand where it is. And some of these sensors are getting better and better at returning environmental data. For instance, the water column sensors that you saw can tell you a bit about these gas plumes. They can also tell you a little bit about the gradients of change in the water. And so you can use those things to form models of what's actually going on in the ocean, and therefore to use that data for environmental applications.
Could you map an oil spill?
In a way, yeah. In a way, you can actually characterize the body of oil and sort of the distribution of some of these particles in the water and then start to map it. It's hard, of course, to map the evolution of the oil spill over time, though. And I think that's what people struggle with.
Here's a question you may understand what he's referring to here. To map the oceans, would they use USVs or do they have ships with a full crew?
Both. There's undersea vehicles, and there's also a lot of the most high-resolution survey work now is done from ships with full crews. And in fact, ship time is extremely expensive. So running a ship is several tens of $1,000s per day for a reasonably kitted out vessel, and it can get even worse. So but it's a mix of both. Primarily, I think most of the high-resolution survey work now is being done by ship-mounted sensors. I could be wrong.
Somebody asked here, what ships does CARIS get its data from?
We don't we don't actually get it from any specific set of ships. Our clients basically own ships. So, like for instance, the CHS has survey vessels, NOAA has survey ships, and they provide us with data to try our software out on. But primarily, what we do is sell the software to those clients to process the data themselves.
Matthew Code wrote, "How deep will the ship's sonar register data, and how accurate is the data?"
Wow, that's a good. A modern sonar system can easily go several thousand meters. I'm not sure of the actual maximum depth that a sonar system can survey, and the accuracy of the depth of the measurement changes with depth, because as you project these beams down, if you only have so much coverage, the beams disperse a little bit as you get further and further down in the water column. So in shallow water, you can get within several centimeters actually, or even smaller amounts of data, or smaller resolutions. But in deep water, it can be several meters.
I think I saw a question earlier asking about what might interfere with sonar, sharks or
yeah, sure.
debris.
Anything actually. Ships, sunken ships, debris, fish. You can actually use sonar to identify schools of fish. There's another actual application of sonar systems. And particulate matter in the water. And so there are a huge number of factors. And so surveying is actually kind of tricky work, because you've got to make sure you get the measurements right, and a lot of things can interfere with that process.
Did you mention that the British Navy uses your information?
Well, I think the British Navy uses some of our software, but it's the UK Hydrographic Office is one of the prime users of our tools for charting.
What about Canadian?
The Canadian Hydrographic Office also uses our tools to produce their charts. So most, if not all, of the Canadian charts are now produced with CARIS tools.
So is it fair to say you work with the Navy to map the ocean?
The Canadian Navy?
Let's presume, yeah.
Yeah, yeah. Well, we don't, as I say, we usually just sell the tools to them and work to equip them with those tools so they can actually do their work.
Did you start off, just one last question for me, I think you started off by saying we know space better than we know the oceans?
Yeah, and it's sort of one of those things to say in a way that we've mapped the moon in more detail in a way than we've mapped the ocean. We really only know publicly about 3% of the area of the ocean has been mapped. So there's this great, and the reason for that is basically that ships tend to stay in shipping lanes, and so they don't really diverge out from that. And that's a very, very small percentage of the area beneath the surface of the sea. So we literally have no idea what's going on outside that boundary, except from now we have some satellite measurement techniques that can be used as well. But at high resolution, we know very, very little about the surface of the seafloor.
Would you like to be there one day where you can Google street map the
Yeah, I think
I
think that'd be incredible. I'd like to one day see a kind of map that actually updates in real time, where we're kind of constantly getting updates and you can almost see the surveys happening as they happen. I think that would be a real dream.
It sounds like you have your work cut out for you for like a long time.
We'll be busy, yeah.
Dr. Masry, that was excellent. Thank you so much. And I'd like to give you this gift on behalf of everyone. Thank you so much. Take care.